get the recorder going. All yours, Ward.
Okay, hang on a second. There we go. All right. Good evening, good afternoon, good morning, wherever you are. I'm Ward Silver, N0AX, and I'm pleased to be invited to give my talk on grounding and bonding. It's turned out to be quite a popular presentation about a popular subject. So let's give it a try. And we'll jump over here to sharing my screen, and I will give you a slideshow from the beginning. I said I will give you a slideshow. There we go. Okay. All right. Now, let's see. I want to make one little tweak here. There. Okay. Welcome to Grounding and Bonding for Home HF Stations. This talk was originally sponsored by Contest University, which meets at Dayton every year before the Hamvention, and it's an all-day program, which is also sponsored by ICOM America. So I'd like to thank both of those organizations for sponsoring the talk and giving me permission to give it to people who ask for it. Okay, the goals of this session are to understand ground and bond. What do these words mean, and why do you care? And by doing so, we'll appreciate the different requirements for AC safety, lightning protection, and RF management in your station. I'll discuss issues and techniques for home stations using HF primarily. Some of this applies to VHF, of course, but this is mostly an HF station type of talk. I guess 6 meters is right in the middle there. So let's call it HF plus 6. We'll also talk about how building a common system allows you to satisfy all the requirements for AC safety, lightning protection, and RF. You don't have to do this 3 different times. And then I'll provide comprehensive resources throughout the program, which is being recorded so that you'll be able to go back and look at it later. You don't have to write down all the URLs and titles. So who is this talk for? The HF plus 6 station owners who are building a new station. As a matter of fact, that is the best time to talk about grounding and bonding because you don't have stuff already in place. And you can do it right from the start. You don't have to disassemble or take anything apart. Maybe you're upgrading a small station. You start with a couple of radios on the desk, as we all have, and pretty soon there's the third, and then some accessories and so on and so forth, and a couple of more antennas, and it's time to rebuild. This is a good time to talk about grounding and bonding. Oh, you added an amp, and suddenly there are all kinds of new issues in your station with RF management and that sort of thing. So this is also a topic of interest to the new amplifier owner. Or maybe you live in lightning country and you're interested in keeping Mr. Lightning outside the station and preserving your equipment in the home and the station. And maybe you're just trying for better performance and you want to see if your grounding and bonding system is up to snuff. So that covers the audience. Ham radio references the 2 primary reference books, ARL Handbook and ARL Antenna Book. Both have a lot of information about grounding and bonding. I've been editing those books for some time now and have endeavored to get a lot of safety and basic good practices for station building in those books. Also the NEC Handbook. Many of you are familiar with the National Electrical Code. The code is actually a small book. It's full of legal definitions organized in chapters that are called articles. And what you really want is the National Electrical Code Handbook, which is considerably larger. It's a very thick book, and it takes everything that the NEC has in its various codes and rules and expands them into all sorts of text and discussion and drawings and figures to help you understand what it's supposed to do. Any one of the recent editions is fine for amateur radio, and these are typically available at your library, and you can go in and copy of the articles that you need and take them home. But you want the NEC handbook that's available online, used and new. Also, lightning protection for the amateur station was written by Ron Block in R2B. Ron is associated with Polyphaser, and he wrote a 3-part article in QST of June, July, and August in 2002. These are freely available on the ARL website. They're very good articles. Ron was one of the reviewers of my grounding and bonding book. Another good reference is written by Jim Brown, K9YC, and there are 2 listed here: Power, Grounding, Bonding, and Audio for Amateur Radio. Jim's a retired audio professional engineer. And the second one, RFI, Ferrites, and Common Mode Chokes for Hams, is another excellent tutorial. Jim's published a lot of information on his site, and it's a good one to have bookmarked. Tom, WHJI, has a 300-foot tower on top of a mountain in Georgia. He knows a lot about lightning. So I suggest that you look at Tom's web pages on ground systems, and there's his URL. Those are good references. Certainly there are more. Those are good starting points.
Hey, Ward.
Yes.
Should guys ask questions as you go through it, or should they wait till the end?
Let's wait to the end for questions.
Perfect. Thank you.
Because sometimes I'll answer them as we go through and it becomes more clear. So let's save them up for after the show. The background reference I'm most familiar with is Grounding and Bonding for the Radio Amateur. It was written a couple of years ago. It covers AC wiring, lightning protection, and RF management. It came out of a couple of columns in Hands-On Radio that was a QST series that I wrote covering about 15 years. And these topics generated more correspondence than any other topics throughout that series. So I suggested that we try to capture the information that's sort of spread out among a bunch of different references and put it in one book for people. It was reviewed by a number of experts, including the ARRL lab. I'm not a total expert on this, but I know people who are, so I got them signed up to keep me out of trouble and make sure that what we put in the book is correct. So far, so good. And there are a lot of numerous examples for you to use as you build it. As you'll find, this is not a cookbook talk and it's not a cookbook topic. There are some certain safe practices that you should follow, but everybody's circumstances are different. So this is basically a toolbox of things for you to use in your station. So let's jump in there. What is ground anyway? The word ground is way overused. We tend to throw it around and it has different meanings. It can be a noun where you talk about ground is actually an earth connection. It's the ground. And that's typically how you talk about it in the world of AC or lightning protection. It can also be just a local reference potential. You see ground symbols on circuit schematics. It might just be a local reference connection. For example, an aircraft system has a ground, but I don't see any of them dragging a chain, so they must refer to just the airframe of the aircraft. In RF, what you're talking about is a local reference potential for ground. It can be a verb, which is an action. In other words, I'm going to ground something. And when you say I'm going to ground something, you mean I'm going to connect it to the reference potential that exists for this circuit or system. It might mean connecting something to the earth. It might just mean connecting something to an airframe or a car frame, or it might just be connecting something in an electronic circuit that's battery powered and has no connection to the earth at all. It can also be an adjective, which describes a type of connection, such as a ground conductor or a ground system. And it can mean all of these things at the same time. For example, in the sentence at the bottom, I'm grounding the chassis to ground with a ground wire. So we've used ground 3 times, and it has different meanings for each time. So you have to be very careful when you use the word ground to make sure that you understand and your listener understands what you're talking about. The British have changed earth connection to earthing, and they talk about earthing something or an earth connection. They don't use ground. and that helps separate things out. But we use ground a lot. A couple of myths about ground. The Earth is not a magic sink into which we can pour RF or lightning and expect it to magically and safely disappear. It's not like we put in a ground rod and run a wire to it and suddenly, lo and behold, everything's at 0 volts. Doesn't work that way. The Earth has electrical properties just like wires do. And so we have to treat the Earth as sort of a big distributed resistor. And it's not really a 0 volt at any particular frequency. So it can be a reference potential, but it may not be 0 volts, and certainly not at all frequencies. There are a lot of fuzzy definitions. RF ground is a word that gets, a phrase that gets thrown around. There basically ain't no such thing as RF ground. There is no way that you can make a point or a surface 0 volts at all frequencies in RF. About the most you can do is create a consistent reference voltage across a range of frequencies, voltages, and currents. So I try to keep people from using the term RF ground because it implies more than it is. The other is ground loops. AC guys, the electricians, they don't like ground loops because that allows error currents to flow, and the error currents can be quite large. Audio guys talk about ground loops because magnetic fields will induce voltage in a loop, a closed loop, and that causes a current, and that causes hum or buzz. But generally, if you look behind your equipment, any connection, pair of connections between a couple of pieces of equipment create a ground loop. There are hundreds of ground loops, and even the small stations, and we're not going to get rid of them. So basically, you have to manage what you're doing with your cables and your connections. So I tend to not use the term ground loop, except in very specific instances. The other is single point ground. It depends, as we'll talk about in a minute. Single point means many different things. A single point means a very different thing to the AC electrician, where the frequency is 60 hertz and the wavelength is about 5 million meters. And it means a lot different to the RF guy operating at 10 meters, where the wavelength is 10 meters. Imagine that. And so you have very different perspectives on things. So when you say these things like single point ground, you have to make sure you qualify it. Okay, let's talk about bonding. That's the partner to grounding. All that bonding is a connection intended to keep 2 points at the same voltage. That's all it is. So that everything goes up and down together. If you have a boat and you have a floating dock, why does the dock float? So that everything can go up and down together when a wave comes by, and it doesn't cause one boat to go up and one boat to go down, or cause damage to the dock or the boats. You want everything going up and down together. When there's a current surge or some kind of lightning or a fault, you don't want this point to suddenly be 6 kilovolts above this point. And if you can keep everything at the same voltage, what causes current to flow between 2 different points? Voltage. So you can minimize current flow by minimizing voltage differences. Bonding in the AC world prevents shock hazards from voltage differences. If you bond all your equipment together with suitable conductors, then it's all going to be at the same AC voltage, even if there's a short circuit. So the idea is to prevent you from getting a shock with when you put one hand on one thing and one hand on another thing. You don't want there to be voltage differences there. In lightning, you want to prevent the destructive voltage differences caused by lightning surges. And you hear stories about suddenly a giant arc jumps between one point in the house and another point, and now nothing works. It's because the pieces of equipment were not bonded together, so that suddenly there was several kilovolts of voltage between the two of them, and there was an arc, and that caused the problem. So you prevent the destructive voltage differences from lightning by bonding things together. And as I just mentioned, you limit current flow between the devices caused by voltage differences, and that's what causes RFI. It's not the voltage, it's the current, and the common mode current that flows into things where it should not flow into. And if you can prevent the current flow by limiting the voltage differences, you're miles ahead. So it accomplishes three things: prevents the shock hazard, prevents the destructive voltage differences during lightning transients, and it limits the current between devices in your station caused by RF pickup. It sounds hard, but it's not. It's simply something that you have to put on your checklist of things to do when you install or change your station configuration. You put in a new piece of equipment or you move things around. You have to think about it and go, okay, how am I going to bond all this stuff together? And then it sounds expensive, like we've got to do welding, or we have to use some special copper bronze thing, or super expensive clamps or something. It's not at all. You probably got all the materials right in your station already, and it's really pretty straightforward. But it does require to use the right connecting materials and hardware so that the bond stays in place. This is particularly true when you're working outside and you have buried conductors or ground rods, or you're bringing things in and out from outside. When you bond your equipment together, it works in your favor for all three areas that we have requirements for: AC safety, lightning protection, and RF management. So by an effective bonding program in your station, you're going to solve a lot of problems or keep them from happening in the first place. For bonding to work, it has to be low impedance and it has to be electrically short at the frequencies of interest. Ham radio covers an awful lot of frequencies, all the way from 60 hertz or 50 hertz if you're in Canada, all the way up to light, microwaves, whatever. So we have to consider when we're bonding in our station, what are we trying to accomplish? Is this a low band installation? Are we talking about 10 meters? Are we talking about 6, 2, 70 centimeters? What? The connection between the equipment has to be short so that it doesn't start acting like a transmission line. It also has to be low impedance so that if current does flow through it, it does not develop voltages from one end of the bonding conductor to the other. It also has to be heavy enough to carry the expected current. If we're talking about AC safety, where there might be short circuits connected to a branch circuit, where you might have a couple 100, 300 amps for a short period of time, the idea is that you want the bonding to be heavy enough to carry that until the protective components remove the power from the circuit. If you're talking about lightning, then you have to be really heavy because we're talking about kiloamps. I don't know about you, but the concept of kiloamps is a little intimidating, and you want to make sure that the wire or the strap or whatever, the pipe, the bus bar is big enough to carry the expected current. That's especially true when you're outside working on your tower or antenna system. And it has to be sturdy enough to survive in the environment. Typically inside the station, that's not a problem. Outside the station, that can be a big problem because you're burying things and you tend to forget about where they are. You have to, for example, if you have a buried grounding conductor outside, it has to be sturdy enough to survive when you rototill it up for the garden or dig it up with a shovel to put in a new tree or a bush. I don't think you have to ask how I know that. So if you don't use heavy enough stuff, you can cut right through it. It gets driven on, there are frost heaves, all these other things. It can break and you would never know that you don't have a ground connection anymore. That's one of the reasons why when you look at your building codes, it talks about number 6, number 8, number 4, big, heavy stuff. Inside your station, you can use a lot lighter stuff. The standard used by everybody that builds installations, and that's commercial and military, is solid strap, 20 gauge strap, copper strap. You can get flashing and rolls of flashing and cut it up. And standard is about 1.5 inches or 2 inches. If you've got a relative in the roofing business, you can often get scrap flashing from them, or you can use heavy wire. And when I said you probably have the necessary materials already in your station. I know we're hams and we never throw anything away. So all that N0AX, the little 6-foot pieces that you kept in a box because you might use them someday, these are great stuff. They're perfect for bonding. So take that piece of N0AX out, strip off the jacket. You've got a ground wire, you've got a hot wire, you've got a neutral wire in there. These are great for bonding, and they don't have to be bare. You can use insulated wire, it's fine. If your equipment needs to move around, say you have a rolling rack, or this is mounted in your car, or maybe the equipment vibrates for some reason, you can use the flat weave tinned braid for grounding and bonding purposes. It's that silver stuff you can buy at Hamfest. Do not use exposed braid from old coax because it deteriorates. The instant you take the braid out of a piece of coax, it begins to loosen up. So all those little wires that are braided and lay over each other, they're held in place by that jacket. The minute you take that jacket off, they start to loosen up. And as a matter of fact, we usually loosen it up to get the center conductor out. That means all of these little wires that were at one time held in hard contact with each other are no longer in hard contact with each other. Furthermore, the braid is no longer protected from oxygen or water, so it begins to corrode. And it might work for a little while, but after weeks, months, whatever, you start to have, instead of a nice solid ground connection, you have a whole bunch of little disconnected wires, and that's not good. You get noise and stuff. If you want to use old coax, just leave it in the jacket. Treat it like a cable. Waterproof the ends, twist it into a pigtail, put a terminal on it, and just treat it as a big wire. That's fine. And never use braid where it will get wet. Even the tin stuff, wet braid or exposed to corrosive chemicals of any sort will corrode. You'll wind up with a whole bunch of nonlinear junctions. Each one is a nice little mixer. So you really don't want that stuff. Use the flat weave braid if the equipment moves around and it's dry. Otherwise, use strap or heavy wire. Okay, safety grounding. Depending on where you live in the country and how old your electrician is, the grounding conductor can have several names. The equipment ground is the current term in the NEC. It's also called third wire ground or green wire ground. That is the connection back to the AC service box. You've got to keep ground connections low resistance. The wavelength is really long, frequency is really low, so inductance really doesn't count that much. The purpose of this connection is twofold and twofold only. It provides a path back to your AC common point for fault currents. That's short circuits and leakage. And so the idea is to give that current a path so that it can trip the protective components and they will remove power from your circuit. Leakage currents from compromised insulation or from excess capacitance also should go through the ground connection and not through you. It also stabilizes the AC power system voltage during faults or transients, such as lightning hits a power pole, or there's an auto accident or something. All those connections to ground rods and butt wraps around the pole stabilize the power system so the voltage doesn't swing around wildly. So there's only two reasons for this AC safety ground, and those are it. Neither have anything to do with RF, and they are not really very effective at lightning protection in your station. Here's the AC service common point, a typical service for a house. You've got your two phases, a grounded connection at the pole, at the transformer, and then the neutral goes into your service panel. If you open up the panel, you look inside, you'll see two buses. One is the neutral bus where all the white wires go. One is the ground bus that's bolted directly to the metal service box, and it has all the ground conductors, the green and bare wires. Often, almost all the time in major service entries, like in your house, the neutral and the ground buses are tied together with a main bonding jumper, and then that's tied to your grounding electrode outside, which is one or two ground rods. So that that is the common service point, and that's where the fault current needs to go in order to trip the breakers. If you don't know what you're doing, and I know we're ham radio operators, but if you're not sure what you're doing, get a how-to reference. This is a very good one. It's inexpensive. It's about 20 bucks. It's available at the big box hardware stores. It's available online. It's an excellent expenditure of 20 bucks. I know we can all put in a branch circuit, and some of us are really good and can even do a three-way light switch, but there's a lot of strange electrical equipment out there, all these weird dimmers, all these different appliances. This book shows you how to do it properly. What's especially important for hams is a lot of us put in sub panels for our stations out in a garage or maybe in an outbuilding. There are special rules for sub panels and outbuildings to prevent you from being electrocuted outside. So find out what those rules are and wire your stuff up that way. There are reasons for that particular practice, and I suggest you all follow them. I learned a lot when writing this book about grounding and bonding, and that was one of the things I went, wow, I had no idea. You can either hire a pro electrician to do the work if you're uncomfortable with it. Sometimes you can just bring one in and have him inspect your work. It's always good to have a pro come in and look over, say, you know, you really need to do this. Instead, you need to move this over here. You need to get this away for this, or please don't connect that ground here, something. These guys know what safe practices are. They're not there to make your life difficult. They're there to make your life longer and not burn down your house. And always remember, your local code is the law. You're supposed to do it. It's not there to make your life difficult. It's there to prevent property damage, and the codes are usually based on the NEC, but if you got special rules because of special soil or a special power distribution system, those rules will be in the code. So, okay, let's talk about lightning protection. You can't steer lightning, but you can help him make good decisions. Mr. Lightning comes from thousands of feet in the air, and it doesn't really care if you move things a foot apart. It's just going to jump right over it. But what you can do is help lightning get to where it wants to, and that is to the earth. That's the whole point. So by creating heavy direct paths to the earth, that allows this lightning charge to dissipate into the earth. That's what you're trying to do with lightning protection. For lightning protection circuits and conductors, inductance is more important than resistance. The voltage caused by a changing current is equal to the rate of change of the current times the inductance. Even straight wire has inductance. You can get, I think, 300 nanohenries per foot, and under a typical lightning surge where you're talking about kiloamps per microsecond of change, you can get hundreds or thousands of volts just between one end of a straight piece of wire and the other. So you want to minimize inductance. It's not so much the resistance, it's inductance. So straight, wide, low inductance paths. All these paths that you want lightning to follow should be outside your house. Don't run them through your call space. Don't run them through your station. Don't wind things around inside the residence. The path should be outside. Don't make it easy for lightning to go through your station on the way to the earth. Mr. Lightning will happily go right through your house, right through your shack, and blow everything to smithereens on its way to the earth if you give it a good path to do so. So when you're worrying about your lightning protection, put those paths outside. Also, create a perimeter ground. All of these different services that come to your house, the antenna you put on top of your house for TV or whatever, all these things are required to have their own ground electrode. The AC service panel will have a ground electrode. It's typically 1 or 2 ground rods. Your telephone service has to have a ground connection. Your cable TV or internet has to have a ground connection. And everybody comes in, puts in their ground connection, but they all have to be bonded together outside the house, all of these ground rods. Why? If you rely on dirt to connect these ground rods together, what is the resistance of dirt? It's a lot. Okay, so if you get a big lightning surge with hundreds or thousands of amps, and it's going from one ground rod to another through the dirt, say you get 20 ohms and 1,000 amps, that's 20,000 volts between your ground systems. That's why stuff blows up inside your house, even though you didn't see the lightning come in and hit it. Suddenly your AC service ground is 20,000 volts different than your telephone or your computer or your TV. Yeah, there's going to be some damage. So what you do is outside the house, run a big, heavy bonding conductor, number 6 or bigger, between each one of the ground rods. And if it's a long run between ground rods, more than 10 or 15 feet, put in another ground rod. Yeah, it's a pain in the neck, but you only have to do it once. Use burial rated clamps, better yet, use the one-shot CAD welds. Those are fun. If you like fireworks, CAD welds are for you. But you create what's called a perimeter ground outside your house where all the grounds are tied together. And that means all of the ground systems, telephone, lightning, electrical panel, ham station, FM antenna on the roof, all that stuff is tied together so it has 0 volts. Everything goes up and down, and there's 0 volts between all these different systems. Okay, here's an example of lightning protection and where the ground path should go. The ground path should go around your station. This is what not to do. You've got a tower outside, lightning either hits it or gets close to it, current flows down the tower. Remember I told you about the inductance and voltages. So here comes the lightning current. It comes up to this nice entry panel that you built. Sure, you've got some antenna lightning protectors there and a ground rod. Okay, so some of the lightning goes through there, but it's just like any other current and divides according to the resistance of each path. Well, if you've got this nice big connection into your radio room, some of it's going to go there, and then it's going to go through the AC service entry and out to the ground electrode over there. And it might toast all kinds of things on its way. So try to avoid this. Here's what a perimeter ground buys you. So this time Mr. Lightning hits the AC power lines. Here it comes. You've got a big transient. It goes through your AC service entry and it goes to your the ground rod out there. Now it might go through the branch circuit, but you've given it this terrific, big, nice station lightning protection ground with lots of ground rods, very low resistance to the soil, which is where it wants to go. So most of that lightning is going to go into your lightning perimeter ground. The tower is connected to it, your service panel is connected to it, all the stuff in your house is connected to it. Give Mr. Lightning what he wants, a big, heavy, direct ground path to the earth. Okay, lightning protection. Rods and radials. Here's your tower. How do you protect a tower? I think everybody's seen the picture in the handbook where you've got a triangular lattice tower. This is looking down onto the tower. Each leg has a heavy connector that goes to a ground rod, and then those are all connected together with a ground ring. That's a great thing. If you really want more protection, run a big heavy radial out from that ground rod another 30 feet or so and bury it. Put in some more ground rods along it. The guys that do cellular towers have told me when we get a rocky or sandy installation, we get a lot more mileage out of burying radials than we do out of ground rods, because that helps the lightning charge get to the earth and it divides among your radials, and that's in your favor. When you're running feed lines along your tower, bond the feed lines to the tower every 50 feet. Because of the inductance of the tower, it's not uncommon to have well over 10,000 volts between the top and the bottom of a 50-foot tower. So you want to bond your feed lines to that tower so there's no voltage between the outside surface of the feed line and the tower. It'll arc through the jacket and you'll get pinholes or splits, and it'll ruin your feed line and cause you to pull your hair out trying to find out why that feed line doesn't work anymore. If you've got a spark gap for an insulated base, if you have an insulated base tower, put a spark gap across it. Just a couple of pieces of heavy wire spaced a little bit, just like when we gap a spark plug for a few thousand volts. Let the lightning arc there and not in your house. Okay, and you create a single point ground panel at your station entry. All this is a sheet of metal. It can be flashing, copper, aluminum, whatever, on a non-flammable piece of material that is at your house, and you run all of your unprotected circuits to it. An AC receptacle to run your station off of. That would go to a branch circuit back to your AC service panel. You've got an antenna line coming in. That's where you mount your lightning protectors. You've got your telephone line or your data service. And then that panel is then heavily grounded or grounded with a heavy conductor to your perimeter ground system. And then from the panel, you run your protected cables, your power, your coax, your telephone, your feed lines, all this stuff, and lightning protection ground conductor. Those all go into your station. Keep the protected stuff away from the unprotected stuff. Otherwise, the unprotected stuff will arc over to the protected stuff, and you'll wind up with damage in your house or your station. So you want to make sure that you connect your RF grounds in your station, the ground plane that you use to bond everything together to this single point ground panel. Here's some examples of what I'm talking about. A protected line duplex outlet. There's from Isobar. You can buy these in various sizes. They have transient absorbers inside. So basically you plug one of these into a branch circuit and mount it on your single point ground panel and plug everything into that. Down at the bottom are the lightning protectors or lightning arresters, antenna protectors, whatever they're called, that we're familiar with. Some of them have a capacitor in the middle of those two connections, and that is to cause the gas discharge tube inside to arc over a little closer, and it clamps the voltage. But that capacitor will block low frequency and DC power if you're sending it out to the tower. So if you're depending on sending operating power or bias down a feed line, make sure you get a DC connected antenna protector. Don't ask me how I learned that. And then the thing up on the right, you can see the various protective components inside a box that protects a telephone line. Here's an example of a single point ground panel at my station. I have one of these at each tower base of the 3 towers. It's in a surplus electrical box, big fiberglass box. You can see my flashing there, and I've got a remote coax switch attached to that. Over at the left, you can see the big ground wire that goes to the ground for that particular tower. Over at the right is a terminal strip. The little blue things are gas discharge tubes, and that's my rotator control cable connections. Here's a tip that's worth the price of admission. For these long runs of rotator cable, you can use 10 conductor irrigation cable. It's rated for direct burial. These are solid number 18 conductor. It's sold by the ton. It's dirt cheap, and you can double up a pair of the conductors and still have a total of 8. You double them up for the solenoid circuit, and the rest of them are for the motor and the control pot. So this works great. Saves lots of money. Save the budget for the fancy rotator control cable to go in your house or up the tower. Here's another example of a single point ground panel. This is K4RO's single point ground panel. Kirk lives on a hilltop in Nashville and was losing a lot of equipment. Every time a big storm came through, something would get blown up. So he basically made a big single point panel in his garage. His shack is directly above that panel, and you can see over at the right the big heavy ground wire going to the ground rod outside. Everything that has to do with his antenna system is tied to that panel. His switching, his filters, all that stuff. And since he's installed this, he hasn't lost one piece of equipment to lightning strikes. Here's my station. My single point ground panel in the station is a rack. Everything is connected to this rack. It's tied together with heavy wires, as you can see at the back on the right. One wire goes outside through the wall to the perimeter ground system, which is just a few feet away. I have 2 operating positions. We'll look at those in a second. Each one has a heavy wire conductor that connects directly to the single point ground. So they're all tied to that point, and that goes outside. Okay, finally, do get a copy of Ron Block's QST articles from 2002. They're freely available to everyone, ARRL member or not. Ron talks about protected zones. You can see a protected zone there with the red line. It encloses everything you want to protect. Every line crossing the boundary must be protected. So that includes AC power, DC power, feed lines, rotator control cables, telephone lines, whatever you got, cable TV. If you want to protect it, that equipment, you have to protect all these wires. Even one wire coming into that without protection will conduct lightning energy into that zone and cause damage. And then you want to protect your stuff in your station by bonding it together. Okay, let's talk about RF management. The first thing you have to realize is everything in the station is an antenna, everything. You're very close to your antennas, particularly at HF. You're in the near field. Your dipole is probably less than a wavelength away. So your feed line, your tuners, your jumpers, your radios, your computers, your grounds, everything is part of your antenna system, and it's going to pick up RF. So forget about an RF ground. It's just not going to happen. What you can do is concentrate on bonding. Keep all of your connections electrically short, and that'll keep everything at the same voltage. You want it to go up and down together at AC. You want it to go up and down together when a lightning transient hits, and you want to keep it at the same voltage going up and down together at RF as well. An amplifier which creates high RF field strength requires extra attention to bonding. And as we probably all learned the hard way, you put in an amplifier, you find all the weak spots. So if you can attack this first with bonding, you'll save yourself a lot of problems. And you do this by creating a common reference plane or bus. Sometimes it's called a bonding bus in your station. We've all seen this picture in the handbook over the many years. It's finally evolved to the point where my lightning consultants are happy with it. Yes, you want to use ground clamps on this 1/2-inch copper pipe, just like on a ground rod. Hose clamps are not made for consistent electrical connections. They loosen up. They look tight when you leave, but they immediately begin to loosen up. So use ground clamps and heavy wires like we talked about before. Bonding inside the shack eliminates those hot spots and reduces audio buzz and hum, which is very important for the digital modes that we're all using right now to work, or in my case, not work, Europe and Japan on 6 meters. Reduces RFI from common mode current, as we talked about before. By bonding everything together, you have 0 volts between point A and point B, so you have 0 current between point A and point B, or at least minimal. And it also reduces sensitivity to physical configuration, so you can move the equipment around and suddenly you don't have crazy business going on at 15 meters. You want to use short or coiled cables. Use the bonding bus and the reference plane to establish that common voltage for everybody. You minimize the loop area because the bigger the loop, the more voltage is going to be induced in the loop. Keep your cables together. Run them along your ground connections and the bonding bus. Always use shielded cables even for power, and use short straps or wire. Here's an example. This is one of my operating positions. You can see the ground plane under the equipment. It's basically aluminum flashing that's screwed to the table. And I lay all of my cables on it. Everything is bonded either to the copper pipe back there or directly together, or to that flashing. And then the flashing is then tied to the single point ground. And finally, your ground system, all currents flow on all wires. So your AC fault current is going to flow on all wires. Your lightning is going to flow on all the wires. It doesn't separate. AC doesn't go, oh, I can't flow on that. That's not a green wire. Nope, it'll flow on everything. So the point is that a single solid ground system of short, heavy direct connections satisfies all of the requirements we've been talking about: AC safety, lightning protection, RF management, and clean audio. And that perimeter ground keeps Mr. Lightning outside. This is an overall schematic. It's in the book. It shows the perimeter ground, your tower, your various services coming into the house, and all the different connections between them. The idea is to make that ground system solid outside and then keep everything inside at the same voltage. Here's your additional resources. Professional associations, all of these are very good. The National Fire Protection Association, they're the ones that came up with the National Electrical Code. Fire protection. Why did the Fire Protection Association come up with an electrical code? I don't think you have to think about that too hard. The Association of Electrical Inspectors is good for training and guidelines. Mike Holt Enterprises has wonderful tutorials for electricians. Many are free. Polyphaser, you've heard that name. There are a lot of white papers and tutorials. And then the Lightning Protection Institute. Boy, wonder what they're about. Papers and tutorials on lightning protection techniques for the civilian. Here's the big hitters, standards and guidelines for communication sites by Motorola. It's also known as R56. Just search for it, it's available online. So is the FAA document. This is how they build their systems. IEEE standard 1100 is very much not free, but it's available in your libraries. And Mill Handbook 419 is the military's electronic equipment facilities standard. You can read these things. You don't have their budget, but you can look at them and see what they're trying to do and then try to do that with your resources. Other books and materials, Ron Block's The Grounds, KA-RAN, Lightning Protection and Grounding Solutions, and the ARL Technical Information sections. One of the great resources of amateur radio. It's really under-publicized. They have sections on electrical safety, grounding, and light protection, all available to the public. Are we done yet? Yes, we bonded. So I'd like to thank you all for your kind attention. And now I'll stand by and take some questions.
Just use your space bar, guys, for if you want to ask a question.
I think I snowed them.
No.
It's a real fire hose of a talk. You can get the book. A lot of the stuff's in there. The handbook, recent editions, antenna book, recent editions, plus all the online stuff. But the key point is to try to keep everything at the same voltage, so it goes up and down together. If you approach the problem that way, you'll get 90% of it right there.
Bert, I have a question, and it has to do with plugging your radio and taking the coax off your radio and taking your antenna rotator off your box. Do those things help you? Should you do those when you leave the station?
Okay, all of those things need to be bonded together in your station. Whatever you're running the coax to, your antenna switch, your radio, your amplifier, all that stuff, and the rotator, make sure you ground its enclosure in the back. If you want to protect the rotator, you can put in little gas discharge tubes or MOVs on that. But yeah, bond them all to your ground system and bond them together. And here's another freebie tip that I learned. Inside your rotator are a whole bunch of unbypassed rectifiers, either Zener diodes or AC rectifiers or those LED control lights. Your rotator cable makes a tremendous antenna. And so it's going to pick up stuff. It's going to conduct it all into your rotator box. All of those diodes are going to turn into little harmonic generators, and then it's going to go right back out the cable and radiate into your main system. And I found that out when I lived on an island where there were 7 high-power AM broadcast stations. And all of a sudden, when I hooked up the rotator, it was a tail twister box, I heard all of the different stations all the way across 40 meters. And I thought, what? And then I hit the solenoid, you know, the brake thing to turn the antenna. It was perfectly clean until I hooked up the rotator. I hit the solenoid, and all of a sudden, all of that grumbling on 40 meters went away, and it was replaced with 120 hertz buzz. And that is that was at the zero crossing of the AC waveforms, where the diodes could once again act like RF rectifiers. They weren't conducting or cut off. So just open up the box, get a little, I don't know, 0.01, 0.001, 50 volt ceramic, 100 volt ceramic, and just tack solder it across every diode in that box. And do that everywhere in your station. That includes power supplies, switch boxes, control boxes, audio amplifiers, anything with a cable on it that has rectifiers inside. You've got to bypass them. You don't really care about this until you start operating on 2 bands at once, and then all of a sudden you discover harmonics and all sorts of other things. So the big multi guys have to deal with this all the time. But every time you repair or replace a piece of equipment, bypass the rectifiers, and that will save you a lot of problem in the long run. Sorry, long answer to a different question. That's my specialty in trade.
Thank you.
Question?
Who else is hanging around with a question?
I have a question.
Go for it.
Lightning arresters, I actually have them fairly close to my antennas and tower at the bottom of the base. Is that going to be a problem? They're brand new. I just put them in. Is that a problem?
No, but I would also put some in where they enter your house. I got a piece of property here in Missouri that's on a ridge, and when I walked it the first time, I noticed there were a lot of trees that were burned, and I knew that I was going to get some lightning strikes. So I have a lightning protection at the base of the tower. I have lightning protection in what I call my sacrificial barn. All the feed lines go in there, and there's a big single point panel there with a lightning arrestor. And then that all goes underground to another little doghouse outside the house, where I've got yet one more single point ground panel with lightning arrestors. My lightning arrestor budget was substantial, but the point was to wear out Mr. Lightning by the time he got to the house before he went in. So far, so good. But yes, put one at the base of the tower, but I would also put another one at where it comes into your residence.
How do you know if they're still working or they haven't been hit or something?
Is your house still standing?
Yes.
They're working.
Okay.
You can test those things in a couple of ways. If you can remove the little gas discharge tube cartridge inside, you undo the little brass cap and you take that sucker out and you look at it with a magnifying glass. If it's a clear glass cartridge, you can see the nicely curved electrode inside. If that's burned or pitted or cracked or anything else, replace it. Some guys just replace it once a year after lightning season. They're not that expensive. They just go through and they just replace them all. Or you can test it with an installation tester, take them down to a motor shop, rewinding shop. They'll have what's called a megger, and they can do an insulation test for you and find out if they break over at the voltage they were supposed to.
Thank you.
That's how you do it. The little blue ones that I put on the rotator lines, those are 75 volt units. They're from Mauser. They're about $1 a pop. I bought a box of 100. Oh, I just use them like candy.
25 what?
Go ahead, Steve.
What 75, what's the voltage? Is it 75 volt gas?
It's a 75 volt breakover with a 20% tolerance. You can get lower ones. The problem with using lower voltages is the typical rotators have a 35 volt transformer in them. And so what you wind up with is 1.5 times the voltage. So that's maybe about 50 to 60 volt peak on those things. And the bottom end of the breakover range can fall into that. So 75 volts was about as low as I wanted to go. There are also these things called transorbs that are back-to-back heavy-duty Zener diodes that are designed for this application. And they act very fast. They can absorb a lot of power, but like the other diodes, you have to bypass them with a capacitor to keep them from rectifying RF. But you can use those as well. I'm thinking, I have some, I haven't gotten around to put them on my control pot circuits yet, and those would be 18 volters because the CDE, ham-M, tail twisters use a 13 volt rotator circuit.
So I know a number of hams that run outside and disconnect their antennas every time lightning's in the area.
Sure.
I'm sure it helps, but is it false? I mean, is it sort of false security for them or not?
Not really. I mean, as far as the antennas go, the feed lines, sure. Take them out and throw them outside on the ground away from the building. If you disconnect inside, you've still got that connection to the building. It doesn't hurt to disconnect inside, but it doesn't really buy you much either. The thing about disconnecting your antennas outside is you're still exposed to lightning coming into the power lines and all the different other services. And when lightning hits a tower and it goes into the ground, you can have enormous potential differences between different spots on the ground. And so without a perimeter ground, even if you've disconnected your antennas, if lightning comes down and kiloamps are flowing down the tower and into the dirt, you can still have substantial amounts of voltage between different points with a lot of energy behind it. So it's an incomplete solution. It might save that particular feed line, that particular radio, whatever, but the rest of the house is still exposed. VE7PS had a question.
Yeah, I did. Thanks, Ward. You've answered one of them. Perhaps it would be good if we could get the part numbers for the Mauser, not the transorbs, but the discharge devices for the motor cables.
They're made by TDK, Tango Delta Kilo.
Okay.
And I think they're A81, Alpha 81-75X. And if you'll stand by for a second, I'll go find out. I've got the data sheet someplace here. Well, where is it? Let's see. Well, I found the data sheet for the transorb. The transorb part number is 1.5 KE, kilo echo _0. And then the exact part number depends on the voltage. So search on that and you'll get started. Hang on a second, and I'll find this. Surely to Pete, I've got this. I remember copying it about 800 times, but I always put it in a different spot apparently. Okay, let me see if I can put it over here. Maybe it's in the grounding and bonding. Ideas, topic, and success. Here it is. Okay, the part number is Alpha 81-Alpha 75 X-ray. And then there are several packaging variations, and what you want is the axial, AXIAL lead version.
Okay. If you have time, could I ask you to send that to Paul so he could distribute that?
But if I do it right now, otherwise I'll forget.
That'd be awesome. That'd be great.
Here.
Okay, so that answered the first question. The other one is, I have a lot of vintage equipment here. A lot of it with 2-wire AC cords.
Mm-hmm.
And there seems to be, let's call it discussion about whether to replace the 2-wire cords or leave them in place.
Oh, okay.
And I've done both. There's some I've left in place. There's some I've changed to 3-wire cords. Just wonder what your thoughts are on that.
Oh, my usual comedic response is, do you feel lucky? Some of those have the one side of the line tied directly to the chassis. I don't really do a lot of vintage stuff. What I suggest you do is go to the Antique Wireless Association or look at the chapter. It's typically I think it's called the Troubleshooting and Maintenance chapter of the handbook, number 26. And at the back of that is a big section on vintage equipment rebuild and repair. And you can contact the guy. If it doesn't answer your question, then I suggest that you contact the guy and ask him, and they will tell you, because they deal with this all the time.
Okay, super. Great call sign, by the way. I was VE3AX for a lot of 16 years, and I missed that call, believe me.
Yeah, it's a good one. I just got it off the top of the license plate stack in 1975. I said, give me the next one, and that's what I got. So I'm it. That's me. They can put that one on my tombstone. So there you go. Other questions?
Yeah, this is Paul. Just a quickie. One of the things I'm always concerned about is the electromagnetic pulse that comes from a lightning hit. It's not really at my station. It's but maybe 2 houses down or a big tree. I got big trees around with the station. So I put these snap-on RF chokes all the way along my coax and along my rotor cable, everything like that, over my, from the antenna down into the shack. And I have everything else in the shack is just laced with these RF chokes. Is that going to protect me against an EMP at least a little bit?
No, not really.
Just RF.
Okay, lightning is a wide spectrum event. It goes from DC well up into the VHF region. That's why you can hear lightning strikes when you're waiting for the expeditions to come up on 6 meters, 10 meters, whatnot. But there is comparatively little energy at those frequencies. So it's mostly below 10 megahertz. So RF chokes, unless they have a whole lot of impedance below 10 megahertz, aren't really going to slow it down very much. You're going to wind up with a whole lot of type 73 or 75 or 77 ferrite. I think treat it as a transient to be routed, not so much blocked. Because if you put a resistance in the line, a big transient is just going to blow up the choke and keep right on going. You should probably have one of the whole house transient suppressors that goes between the 2 phases and connects to your outside ground enclosure. And then you need the transient protection, that little protected line duplex outlet from Isobar that I showed in the picture. Those things are not expensive. They're like 30, 40, 50 bucks. And they buy as much energy protection. They're rated in terms of joules of protection, 3,000, 5,000, whatever. Buy the biggest one you can. And you need to be careful about using the term EMP. EMP has a specific meaning. The military deals with that, and that's from something undergoing a hyperprompt disassembly, as they say in the nuclear industry. And those things generate really high frequency, sharp transients, not like a lightning pulse at all. The spectrums overlap some, but if you're talking about protection from EMP, you have a far different situation than the garden variety lightning. So you look at it, if you look at it from a lightning protection standpoint, I think you'll be better off. If you're worried about EMP, and I know you guys out there in the Front Range are all near some really interesting military bases and stuff, just put the equipment that you want to protect inside a metal garbage can and put the lid on it. It's a Faraday cage. It'll protect it from all of that EMP stuff. Problem solved. If you have tube gear, it'll probably survive. A lot of the solid state electronics will be toast, but if you keep yourself spare radio around in a metal garbage can, and don't forget that it's not a garbage can, and fill it up and throw it out. You'll be in good shape. I really don't worry about it too much. I figure I'm going to have bigger fish to fry, as they say.
I put a lot of stuff into metal garbage cans, and it is a garbage can. So.
Yep, a Faraday cage. That's what you want.
Right. The other question was these. I see these lightning arresters that they put on to the rotator for the rotator cables, and I've seen a lot of them inside the shack. I've seen some of them outside the shack, like by the tower itself, etc. Is it one? Do they work? And two, where should I put it?
Well, yeah, they work okay. They, as we saw in that picture with there was the big coax lightning arresters, and then there was the isobar thing, and then there was the little telco protector. The lightning protectors for rotators have small gas discharge tubes in them, and or MOV transient suppressors, and their job is to clamp energy coming in from an indirect strike, but they will not protect against a direct hit. Hopefully they'll blow up, and before the stuff gets to your rotator. But you know, they're good enough. I would put them outside, and if you're really worried about protection, you can add more protective components at the terminal strip on the back of your rotator control box.
Thank you.
I have 3 sets. Every one of those single point panels, the one at the base of the tower, the one in the barn, the one in the doghouse outside the house, has a terminal strip, and each one of the terminal strips has gas discharge tubes on it.
Awesome.
Yeah. So far, I mean, I blew one up before one of the rotator control boxes after I moved in and had stuff kind of going in, and we walked in, and I don't live down there all the time. We walk in, we turn all the lights and stuff on, I flip on all the power in the shack, and a couple of minutes later, Ellen comes up, she says, "What's burning?" And I go, "Huh." And I stick my nose in the shack and I go, "Transformer." Okay, so I go poking around, and one of the rotator control boxes got popped. It blew up the little indicator pot circuit. All that stuff was toast, and the solenoid transformer was okay. That's a heavy one, but the little indicator transformer was toast. So since I put up the gas discharge tubes, I can leave them hooked up all the time. Famous last words, knock on wood. I haven't blown any up in a couple of years now, so I have spares. I call my station the Crawford County Cumulonimbus Discharge Facility, and I'm sure it's been hit more than once, but I guess I'm doing something right. So
Good. Any other questions, guys? Maybe if we can let Ward go, or do you guys have any questions?
Gentlemen, thanks a lot. I enjoy watching your email reflector. One of these days I'll actually work some of that stuff. I don't know what it is about Missouri, but all that good stuff goes right over the top.
Thanks, Ward.
What can I say? All right, 73s.
Thank
Thank
you.
Thank you, Ward.
Thank you.
Thanks, Paul.
You're welcome. Bye-bye.
Thanks.